Hello everyone. In this digital signal processing and discrete time control tutorial, we explain how to calculate the magnitude and phase responses of discrete time systems and filters. First, we briefly summarize the concept of the frequency response and digital frequency. And finally, at the end of this video tutorial, we solve an example. We will consider the system shown over here, and we will explain how to compute its transfer function and then how to analytically compute its magnitude response shown over here and its phase response shown over here. However, before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this video tutorial, as well as more than 400 video tutorials that you can find on my YouTube page, and consequently I kindly ask you to press the like and subscribe buttons. Thanks a lot. First, we give a brief summary of the frequency response. The basic idea is to start from the transfer function of the discrete time system that has the following form. Over here, AK and BK are real numbers or coefficients of the system or filter, and Z is the complex variable that is associated with the Z transform. The frequency response is obtained by substituting Z in this equation by this expression. Z is equal to e to the power j omega, where j is the imaginary unit and omega is often referred to as the digital frequency. Here you need to keep in mind that omega is not the classical frequency that you are used to working with when analyzing continuous time systems. This is the digital frequency, and omega is in the interval from minus pi until pi. That is, omega is in this interval, and you should always keep in mind this thing. The reasons for this will be explained later on in this tutorial. Next, by substituting z with e to the power j omega in the previous expression, we obtain this expression. As it will become completely clear after we solve an example, this expression is actually a complex number, or better to say a complex function of omega. Consequently, we can represent this complex number in the polar form. That is, we can write h of e to the power j omega as m of omega multiplying e to the power j theta of omega. In this expression, m of omega is actually the modulus of the complex number h of e to the power j omega. And m is a function of omega, and m is called the amplitude response of the system. On the other hand, in this expression, theta of omega is a function of omega, and it's called the phase response of the system. The amplitude response is also called the magnitude response. And the magnitude response, together with the phase response of the system, constitute the frequency response of the system. Consequently, when someone asks you to compute a frequency response of the system, you will compute two functions. The first function is the magnitude response, and the second function is the phase response of the system. There are a number of approaches for computing the phase and magnitude responses. For example, we can use the polar form of a complex number to transform expressions in the numerator and the denominator of this function. And from there, we can find the polar form of the complete expression. Another approach for computing the phase and magnitude responses is to represent the complex number h of e to the power j omega in the so-called rectangular form. The rectangular form is obtained by computing the real part and the imaginary part of h. Once we have the real and imaginary parts, the magnitude response is then given by this standard equation. And the phase response is computed by solving this equation. Tan function of theta of omega is equal to imaginary part over the real part. Here you should be very careful when solving this equation. you cannot use arc10 function. You need to use arc10 function to solve this equation. This is very important fact. Keep in mind that. Before we explain how to compute the frequency response, it is important to clarify several important things related to the digital frequency omega. The digital frequency is defined by this equation. That is, omega is equal to omega c multiplying Ts. Over here, omega c is the continuous time angular frequency and Ts is the sampling period of the discrete time signal. Let us explain the continuous time frequency and the sampling period. First of all, the continuous time sinusoidal signals are quantified by the continuous time angular frequency omega c. We can represent the continuous time sinus signal like this. T is time. Omega c is equal to 2 pi over Tc, where Tc is the period of the continuous time sinusoidal signal. Now, let us sketch this signal. Here is time, and here is y of t. The signal looks like this. Tc, that is, this time interval, is the period of this signal. During the sampling process of this signal, every Ts seconds, we take a sample of this signal, where this distance is denoted by Ts, and Ts is the sampling period. After the sampling process, we have a set of discrete time points representing our signal in the discrete time domain. If the signal is sampled with the sampling period of Ts, then the time is actually discretized, and we represent the time like this. T is equal to n multiplying capital Ts, where n is an integer denoting a discrete time instant. In that case, the continuous time signal is represented like this. Y of n is equal to this. Over here, we substituted t with n multiplying Ts, and if we take n and put it in front of this expression or this term, we finally obtain this expression. Over here, this term, omega c multiplying Ts, is actually our omega, our digital frequency. That is, the digital frequency, again, omega is equal to continuous time frequency multiplying Ts, where Ts is the sampling period. Now, here is one very important thing to keep in mind. When analyzing the frequency response of discrete time systems or the spectrum of discrete time signals, the digital frequency is in this range, from minus pi to plus pi. This is due to the several reasons. First of all, when analyzing discrete time signals, we only take into account their continuous time pairs that are in the frequency range from 0 to the continuous time frequency omega s over 2, where omega s is given by this expression, 2 pi divided by Ts, and this is equal to 2 pi multiplying f of s frequency represented in hertz. This is actually the angular sampling frequency, and fs is the sampling frequency only expressed in hertz. The frequency omega s over 2, or equivalently fs over 2, are called Nyquist frequencies. Now let us substitute omega c for omega s over 2 in the expression 8. The expression 8 has this form. Omega is equal to omega c multiplying Ts. Again, here omega c is the continuous time angular frequency and Ts is the sampling period. If we substitute omega c by omega s over 2, we obtain this expression. Now if we go further and we use omega s from this equation and we substitute it over here, we will obtain this expression. Now Ts and Ts can be cancelled and consequently we obtain pi. What is the importance of this equation? Well, from this equation we conclude that the maximum frequency in the continuous time domain that we can analyze, that is omega s over 2, corresponds to the digital frequency omega equal to pi. And this is a very important conclusion. Here's another important thing that should be kept in mind when analyzing discrete time systems and their frequency response. For systems that have a real valued impulse response, the magnitude or amplitude response is an even function of the digital frequency, and the phase response is an odd function of the digital frequency. This means that for such systems, we can only consider the digital frequency in the range from 0 to plus pi when computing the frequency response. However, it's a standard practice to consider the full frequency range from minus pi until plus pi. And we know that the frequency response, that is the magnitude response, is an even function. That is, we only consider the frequencies from 0 to plus pi and we just mirror them with respect to the vertical axis to obtain a symmetric magnitude response. For the phase response, we only do opposite. We take into account that the phase response function is an odd function. This interval is often referred to as the digital baseband or simply as baseband. Another important thing to keep in mind is that due to the sampling process, the frequency response of the system is a periodic function with a period of 2 pi. And this is very important to know that this is in the digital frequency domain. In the continuous frequency domain, the period is omega s. That is, the magnitude and phase responses in the baseband repeat themselves with a period of 2 pi. Due to all these reasons, we only compute the frequency response for the frequencies in the baseband. I will explain the periodicities of the frequency responses in my future video tutorials. Now, let's apply everything that we learned so far to this example. Consider this system. Y of n is the output of the system at the discrete time instant n, and x of n is the input of the system at the discrete time instant n. We want to compute the frequency response of this system, that is, we want to compute the magnitude response and the phase response. The first step is to derive the transfer function of this system. To do that, we apply the z transform to this equation. So what I'm doing over here, I'm just applying the z transform. Z of y of n is equal to 1 over 2 z of x of n minus 1 over 2 z of x n minus 1. Now, we can introduce this notation, and this is the standard notation in control theory and digital signal processing. The z transforms of the continuous or actual discrete time systems are denoted by capital letters. Using this notation and using the simple fact that the z transform of a delayed system in discrete time is simply z to the power minus 1, the transform of the signal in the z domain, and by substituting this, this, and this in this expression, we finally obtain this expression over here. Or, if we now group the terms together, we obtain this expression. From the equation 20, we can obtain the transfer function, and the transfer function looks like this. H of z is equal to z minus 1 over 2z. To obtain the transfer function, we simply divided the output by the input. Now, let us compute the frequency response of this system. To compute the frequency response of the system, we will substitute z in this equation by e to the power j omega, and as the result, we obtain this equation. The goal is to compute the magnitude and the phase of this complex number. That is, the goal is to represent this complex number in the polar form. To do that, I will use the following trick. I will represent this term over here like this, e to the power j omega over 2 multiplying everything over here. So what's the idea over here? The idea over here is to get rid of these complex exponential by using this classical formula. That is, I know that the difference of complex exponentials that look like this is actually sinus of alpha. Well, alpha is the angle of radians. In my case, alpha is actually omega over 2. You can see it over here. So let's use this formula. To use this formula, we will simply do the following. We will transform this expression such that it looks like this. Consequently, I will divide by 2j. Since I'm dividing by 2j, I have 1j over here, and actually I took this 2 from over here. Then I obtain this expression. Now, j is actually e to the power j pi over 2. And finally, I can simply substitute this complete term by this term over here, and I can group these two terms together, and finally, I obtain this expression. Over here, I simply computed this part, and I added pi over 2. From this equation, we can conclude that the magnitude response is actually given as the absolute value of sinus of omega over 2. And this is the magnitude response. Now, at first sight, from this equation, it looks like the phase response is simply pi over 2 minus omega over 2. However, this is not the correct conclusion. Don't fall over here. The ground is very slippery. This is mainly because the sign of this term over here changes when omega is varied from minus pi to plus pi, and consequently in the phase we will have a jump of plus minus pi. This means that when sinus of omega over 2 is larger than or equal to 0, this complex number will look like this. And the conclusion here is correct. The phase is simply the part over here. On the other hand, when sinus of omega over 2 is smaller than 0, the complex number will look like this. I will have to take a minus sign, then I will have the sign over here, and I will have the absolute value. Then this minus sign has to be represented in the exponential form like this, and if I group this term with this term, I will finally obtain the phase that looks like this. This means that the correct phase is given by this expression. For omega over 2 in this interval, I will have the phase that looks like this, and for omega over 2 in this interval, I will have the phase that looks like this. If I simply transform these two intervals, I will obtain this expression, or finally, I will obtain this expression. This is because we are not considering omega values that are larger than pi and that are smaller than minus pi, and this is the correct phase. Now, let's go back to the beginning of our video tutorial. The magnitude response is given over here. The analytic form is given by this expression. It's nothing less than absolute sine function. Here's the phase response. The phase response is given by this equation. Here it is. And here's the graphical representation of the phase response. Obviously, the magnitude response is an even function of the digital frequency, and the phase response is actually an odd function of the digital frequency. Another very important thing should be observed about the digital frequency and the magnitude and phase responses. We can see that this system attenuates the low frequencies, that is the frequencies that are over here. And keep in mind that this number over here, or the end over here, is minus pi, and this number is plus pi. This frequency band corresponds to low frequency, and we can see that the magnitude response is very small. This means that slow signals are not being passed through this filter. On the other hand, we can see that the magnitude response assumes larger values at the end. That is for higher frequencies, and consequently the high frequency will be passed through the filter. I generated these graphs by using a Python script. I will explain this Python script in my next video tutorial. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.